So the first thing that we had to design, both for the unloaded and the loaded motor for single axis, was something to facilitate tuning. So that's really the goal of this software. So the control in the middle that's labeled trajectory parameters specify some trajectory for the axis to follow that's smooth and be a realistic path for the robot in an end goal. You can actually change the control parameters on the fly and switch to any of the axes available, as well as controlling the home position voltage and software limits. The graphs are really there to tell you what trajectory was generated. For example, this is an actual trajectory that was generated by the card. And the following arrow graph really helps tell you by how many encoder counts you're off at any point in time, as well as an RMS following error that gives you some average over time. The multi-axis control was really more for demonstration purposes, so we dropped a lot of more of the details. Most of this stuff is really just multiplying indicators and controls. So you have the ability with this software to do any movement in series or parallel on any combination of the axes, as well as the ability to stop the motors individually or together. The indicators really tell you if there's any kind of error condition or the move has been completed successfully, as well as the actual joint angle and angular velocity, as well as the potentiometer value, which tells an approximate position. One other nice feature in here is that you're able to load in positions from a spreadsheet specified either in degrees, radians, or encoder counts, and you can also change these on the fly and then save them back to a spreadsheet if you want to. Now, we recorded a short video using the software that shows the multi-axis movement being done in parallel. You can really only see it for like the first 4 axes, where the 4th one is that last wrist joint. But you can see that everything is happening in parallel. So the way that this software was written was to first check if the controller has been initialized, because the National Instruments controller requires you to reconfigure the card every time it's either been reset or the computer has been reset. So it does that, and then the main execution is the 3 loops in the middle. The bottommost one, labeled pull for kill, just pulls for the kill signal from the user, and it's in its own isolated loop, so that if anything else hangs, you'll still be able to kill the motors for safety. The first group, the main loop on the top that pulls for home and start move, whenever a move starts or you're going to the home position, these are blocking functions. They stop the flow of execution. So that's why this trajectory data is in a separate loop, so that you can always be reading that. And then finally, if any error occurs or the program ends for any reason, any errors are output to the user. Now Laura will be talking about some of the tests that we ran on the robot.
Okay, so now the software is working, the enclosure box is completed, we can demonstrated ability to move each of the axes. So what's needed next is actual quantitative tests to see how well our controller is performing. The first thing we did is we moved one of the axes by 90 degrees and measured the error, so actually physically measuring the angle that the robot moved. As you can see, the error was less than 1%, so it was quite accurate. And then to measure each axis individually, we moved the axis by 10,000 encoder counts, and then measured the actual encoder count that was reached. So you can see it's 0 for axes 2 and 3, and for axes 1 and 4, it's both 11 and 15 respectively. Now the reason for this error is we took the measurement immediately after the motion was complete, whereas if we waited a couple more seconds, the integral term on our controller would have moved it to the final resting position. And we have not yet tested these for axes 5 and 6. The next test was a speed test. And as we noted in our proposal, our initial speed was to be 10 degrees per second. But we actually measured this by increasing the acceleration and the velocity on our controller until the actual robot was no longer increasing in speed. So you can see that the maximum here ranged between 22 and 56 degrees per second, which is much higher than we had originally proposed. Obviously, the faster the better for making quick movements. So we didn't run into any real major problems with this project. We did run into a couple small problems, which did impede time. And so the first problem we ran into was when we were doing the single motor test. And we noticed that the connections between the motor weren't really that concise. There was some problem with the connectivity, so our solution was to, in fact, rewire those connections, and that solved that problem. The next problem we ran into was when we tried to implement the previous group's code just to use as a base point. The way that they had been running it was to configure the motor as a stepper motor, but it's not actually a stepper motor. So we wanted to do it as a servo motor so we could actually use the encoders and potentiometers as feedback in the software. And for this reason, we actually ended up using National Instruments Flex Motion to instead configure it as a servo motor and use it like that in our actual implementation. And the final problem we ran into was after we had built, fabricated, wired up the encoder box. When we connected it to the software, it didn't initially perform as expected. And after debugging, we realized that the actual problem could be solved simply by changing the polarity of the motor signal. And once we changed this small detail, the software works exactly as anticipated. So as for the cost, we were pretty much on track with what we had proposed. The only difference, as you can see, is with the hardware enclosure, which ended up costing $450 more than anticipated. This was in part due to the fact that we had underestimated how much the actual electronics box would cost in the industry. They're priced quite high. Additionally, we did not take into account small purchases such as the intake vents, the fans, the cable housing, and just small components which ended up adding up significantly. So we did actually accomplish everything that we set out to in our proposal, but there is certainly room for future work, and the future work that we would suggest doing would be first to implement inverse kinematics. It should be relatively straightforward to do with the software that we've provided because it already can read in values from an Excel spreadsheet. So just using an inverse transform matrix should make this a pretty feasible application. The next thing that we would like is to implement coordinated motion on the axes. And what this means is if you want to move several axes at once, one axis might finish before the others, and it would be better if you could tweak your controller so that each of the axes would end its motion at the same time. Right? And finally, our design was originally intended to be mounted onto a cart that includes the robot arm, the electronics box, and the computer which controls it. And it just wasn't feasible to complete that during the semester, but the design and the specifications are all adequate such that this could be done easily in the future. Well, that concludes our presentation. Are there any questions?
I just got two. First of all, when you were talking about the error that you received when you moved the arm, did you take the error measurements after you had saturated the speed of each of the axes?
No.
Okay.
No.
And I noticed you were only getting error on 2 of the axes.
Right.
If you were to, does your code provide for a way to decrease the speed of the arm or specify that kind of?
Yes.
Okay.
You can specify, and as I said, the reason the error was there is because we were taking the measurement immediately after
Right.
instead of waiting for it to settle.
And we haven't done an optimal servo tune on all the axes yet. So that was just a rough tune on those 4.
Yeah, because if you're getting 0% error after saturating the speed, that'd be pretty silly. Like silly good.
Yeah. Pretty good.